Fine.
Welcome, everyone. We are so excited to have you guys, and I'm really excited for this Q&A because we have with us Olivia Lanes, the global lead of IBM Quantum Content and Education. I know Olivia's videos inspired me to join the quantum industry, and so I'm really excited to get the opportunity to have this live Q&A with her. So feel free to put your questions in the chat or in the Q&A box. And I see we already have a lot of questions in the Q&A. So, Olivia, I'll give you a chance to introduce yourself and then we'll go ahead and dive in.
Yeah, sure. So I got to see everybody briefly this morning already, but we were dealing with some technical issues, so maybe I didn't get a chance to introduce myself very well. But yeah, hi, I'm Olivia. I have been the global lead for content and education at IBM Quantum for some number of years now. Before that, I got my PhD at the University of Pittsburgh in experimental quantum measurement. And then I came to IBM very quickly after I graduated, and I have been here ever since. So, some of the things that I like to talk about and think about are quantum education, obviously, but also how do we connect with people who don't necessarily have the same type of educational background that we do, and how do we get more people involved in the quantum computing community in general. So, yeah, happy to answer any questions about my journey or about the lecture that I just gave. I think like an hour and a half ago, anything like that. I think we have like 30 full minutes, right, since Greedy. So,
Yes.
yeah, whatever you guys want to talk about, I'm happy to.
Awesome. I see a fun question that we can get started with, which is what is your favorite quantum mechanics principle if you had to choose one?
Quantum mechanics principle. Well, it depends what you mean by principle, I guess. But without getting too annoying about it, I think the thing that I think is coolest about quantum mechanics is probably the measurement paradox in general, and the idea that what you are observing changes the outcome. I mean, I think that's fundamentally probably the weirdest part for me. So it's my favorite.
No, I like that. I think mine would probably be entanglement, kind of pretty much on the same light year, I would say. The next question is if two particles are really far away, light years, and are entangled, does measuring one instantly affect the other particle? If so, then wouldn't that break the limitation that nothing can go faster than light? Is there any investigation done on using entanglement as a way of instantaneous information sending? I like the way this person thinks, but
Yeah, it's a very optimistic viewpoint and very common. It's not true. So, yes, if we had two particles at opposite ends of the universe and you measured one, the other would instantaneously be affected. However, that's not saying that information is traveling faster than the speed of light because you can't actually control what is being sent. The inherent randomness gets rid of any possible transfer of faster than light communication. Like, huge misconception. People think that entanglement is faster than the speed of light. It's not. It's very fast, but I mean, like, whatever. You can't actually give anybody information using entanglement faster than I could pick up a phone and call you and tell you what I measured. So that's really like the hang up is if I'm just sending you random information, yeah, you can receive that random information, and the collapse of the wave function inherently goes randomly to 0 or 1. But that's not giving, I can't control it. So it's not real information. I hope that makes sense.
no, that definitely does. Our next question is about Schrodinger's cat. Why a cat out of all animals?
Oh, dude, I don't know. Schrodinger was weird, man. He was a weird dude. He came up with the cat, not me. I love cats, so I am personally against the death of cats.
Agreed. Now, another entanglement question. Does entanglement in quantum computing always require physical proximity of qubits, or can purely mathematical entanglement, like in wave functions, be leveraged differently?
Well, I think you might have a misconception over what entanglement truly is. It is a physical phenomenon, and it's not a mathematical construct that you just write down on paper and then you say it happened. Like, they do have to have some physical mechanism in order to exchange information and photons or become correlated with one another. So there has to be some physical connection. However, that doesn't necessarily mean they have to be right next to each other to become entangled. We can entangle qubits from a physical distance, be that in a dilution refrigerator or with lasers or whatever, but there has to be some physical mechanism that connects the two to become entangled. It's not just something that you write down mathematically and say they are entangled.
Got it. And then we had a couple questions related to your career and journey. Did you get into quantum computing by taking specific courses in undergrad? I don't see any quantum computing courses at my school, so how would I get involved more with quantum computing after the summer school?
Yeah, so I didn't take any specific courses in quantum computing in undergrad. It was a topic that was introduced to me at the very end of my senior year of undergrad. I took a lot of quantum mechanics classes, but not quantum computing classes leading up to that point. And then what ended up happening is I had to do a research project in order to have a thesis for my undergrad and graduate. And I did my thesis project on entangling photon states using lasers. And I learned that quantum computing was a thing and that the theory of quantum computing was very closely tied to what I was doing for my thesis project at that time. And I thought it was really cool. And so I ended up just applying to graduate schools that I knew that had strong programs in quantum computing at that point. But I never took a class in it until I went to graduate school. So you don't have to take a quantum computing class in undergrad, but like you can still really bulk up on the fundamentals. And some of the fundamental classes that I highly recommend are, of course, quantum mechanics, linear algebra, lots of good math. But if you're interested in like applied quantum computing, then I would also not shy away from some electrical engineering courses as well. Those are really important.
Awesome. As an electrical engineering major, that's good to hear. Um, and then the top question right now is when do IBM internships open for summer 2026?
Yeah, good question. So it varies a little bit every single year, but generally it's around September. So if you're looking for
Awesome.
an internship next summer, the time to be applying is this fall. So it's a
Yep.
lot earlier than people think. And unfortunately, we always get tons of questions about it in the winter, and we're usually done hiring by that point. So you want to get your application in as soon as possible.
And highly recommend the internship program, and highly recommend that you apply. Hi, Olivia. Which textbooks would you suggest for quantum computing?
So the Bible is Nielsen and Schwang. I know a lot of people will say it's like a really good introductory text. I found it more difficult than a true introductory text. Like the first three chapters are pretty introductory, and then it like ramps up real quick, and those problems are hard. So that's a good, I think, graduate school textbook. But if you're looking to get into it and you don't have a ton of experience from the get go, I really like Tom Wong's book. I bought it on Amazon. It's pretty affordable, but I think he also still maintains a free online PDF version, which I can recommend. And it also just like depends like what aspect are you coming from? Like, are you interested in the computer science aspect? Are you interested in the building quantum hardware aspect? There's another real good book by Ray LaFlamme that came out. I think it's called Building Quantum Computers that I really like, but it's much more applicable and hands-on. And then there's also like a lot of really good free lectures from like John Preskill and Steve Gerwin online, which I personally learned a lot from. So it doesn't have to be a traditional textbook either.
Sounds good. And I will also plug in the Qiskit YouTube channel, which personally helped me a lot as I got
Oh, thank
started in
you.
this
I'm glad.
industry. Awesome. The next question is, was there any knowledge from astronomy or astrophysics that you've applied in quantum physics or quantum computing?
Oh, that's a good question. So I did learn quite a bit of coding when I was studying astrophysics, which, it wasn't in the same language, but you can apply the same principles really. So I think it made me a little bit of a better coder. Um, but that's probably it. I mean, classifying stars was mostly what I was doing when I studied astrophysics, and it didn't really have a lot of applications in quantum computing. So it was a pretty big pivot. But on the other hand, there are some people I'll just mention who are studying astrophysics with a lot of principles that we use in quantum computing, like for the axion search, if you're familiar with that. A lot of people in astrophysics are using dilution refrigerators hooked up with quantum amplifiers, which is what I did my PhD on and built, to try to detect axions and look for dark matter. So there is a correlation for sure. I wasn't involved in that type of research, though.
That is really cool. And I see like a group of a bunch of questions that sort of leads into that, which is a lot of people are asking how they can pivot into quantum computing after being in a specific field, like let's say classical software engineering, and now they want to switch into something like quantum algorithm engineering. Do you have any advice on that or how to build that skill set?
Yeah, so I always feel a little weird answering these questions because it's such a personal answer, I think. And unless I know you or I've seen your resume, it's hard for me to give like what I feel like is really good concrete advice. But in general, I mean, I think the core principles are like you got to take some classes in it. You have to build up your credentials. But you also just need like an in, and it depends what type of program you're interested in or what type of work you want to do in quantum computing because it's a pretty big, expansive, interdisciplinary field. If you're a computer science person, a classical computer science person, and you want to get into quantum algorithms, that's pretty hard if you mean like designing new algorithms. But if you're just talking about like building and programming the software stack, then it's really not that different because you can sort of apply the exact same learnings to classical computers and quantum computers. You just have to learn a little bit more about the funny rules that we have to apply in order to make our code work. So I recommend, trying your hand at Qiskit, getting involved in some projects. I mean, there's no easy button, which is what I think a lot of people um, are looking for, like a direct pathway. There's no direct path. But if you follow like some specific guidelines, like trying your hand at open source, creating some credentials, then I think you have a pretty good shot.
Awesome. And now I really like this next question. What's one thing you've learned from working in quantum computing that completely changed how you see the world, not just as a scientist, but as a person? And then the second part of it is, what's one thing you wish more students asked you about when they meet you at times like this?
Oh, geez, these are really good
I know.
questions. So the first one is, sorry, say the first one again. I was focused on the second one.
No, you're good. What's one thing you've learned from working
Oh,
in
one thing
quantum
I've learned.
computing?
Um, One thing I've learned, and I feel like people are going to say it's a cop out answer, but it's not. It's like quantum computing is both way more accessible and way more difficult than you think at the same time. So I really think that people think that like the bottleneck is the beginning and they hear the word quantum or entanglement. They think, I'll never understand that. That's for geniuses. I'm not even going to try. And I vehemently disagree with that. I think that that is something that basically anybody can learn if you just have the appetite for it. Like I can't force you to learn it, but if you're curious, you certainly can, and you can understand it at least as well as anybody understands it. The really hard part comes when you're trying to do something new in the field. But that's true for research in general. I don't think that's necessarily true for quantum computing specifically. I just think that conducting novel research is in general way harder than maybe you think it is. Like when I was an undergrad and I was getting ready to apply to graduate school, and I was like, oh, well, I might want to do my thesis in this and this and this. And it just ended up being a lot harder than I thought to come up with novel ideas that hadn't been tried before, to find things that people weren't exploring already, and then just to like stay on top of the literature because everything in this food field moves so freaking fast. So that's, I think, the hard part, not the beginning part. So that's, I think, a pretty common misconception. And then one thing that I wish people asked me, which they don't ask me so much, um, this is a broad answer and it's non-specific, but I think one thing I wish in general people understood is that this is obviously also a networking opportunity. And we do a lot of networking opportunities at IBM. And in general, I think it's a really good idea. But you should be networking with people before you're looking for a job and an internship. So, one common mistake that I wish people would stop making is trying to connect with me or a colleague when you have like a specific request, like, hi, I need a job tomorrow. That's not great networking. Good networking should happen months to years before you're looking for a specific opportunity. And when you're just looking for general mentorship and you're looking to connect with somebody and learn from somebody just for like the sake of learning or for the sake of like building a relationship. So if you're just like reaching out to people in the field to try to get something specific for them, it usually isn't going to work out in your favor.
Completely agreed. And that also leads into our next question, which is next steps after successfully completing QGSS 2025. And I know we'll talk more about that as we near towards the end, but would love your
Yeah,
take
we're
on
going
this,
to talk
Olivia.
about a lot of cool next steps for you. I think, if you had a good time, obviously apply for an internship next year, depending on like your geographic location. If you're a student, consider joining the quantum computing club or starting a quantum computing club at your school. We've had a lot of people graduate from the school and decide like, my school doesn't have these opportunities. I'm going to make them myself. And that's always extremely rewarding to see. And those people do extremely well, I would say, in their career in the long term because they build up this intuition and skill set about like managing a club and also just like starting something off on their own as well. So I super encourage that. There's a lot of independent learning you can do on the IBM Quantum Learning platform, which I certainly encourage. There's some more advanced stuff there too. If you've just sort of like whet your appetite and you're like, I'm looking to get more involved in something technical in this path, go check out those courses. And then videos as well on the Qiskit YouTube, like since Grady already said. I think the Qiskit YouTube is a great learning place. It depends where you want to go. I'm sorry, I keep saying it depends, but it's true.
Awesome. And our next question is about cybersecurity. I've learned that quantum computing poses a great threat to current information security infrastructures. What are possible measures to mitigate this threat? And is it possible to come up with a classical algorithm that a quantum computer cannot solve in polynomial time? So I guess that's sort of two parts.
Yeah, so that's certainly true. Quantum computing could pose a threat to traditional security on computers. But luckily, IBM has been working with the National Science Foundation and a lot of other government entities and companies as well to come up with some quantum safe algorithms, which we are working to implement broadly over the next few years. So we have a plan. We know that this sort of D-Day of encryption, or Q-Day, some people call it, is coming, but we have ways to combat that. And we have algorithms that we have already invented, that IBM has invented, actually, that we just need to encourage others to implement. And, on a pretty fast timeline, I would say. We're working with the government to try to do that as quickly as possible.
Awesome. Now, what would you say to people who say quantum computing is all hype?
Um, I would say I understand why they feel that way. And the field has not done the best job of science communication. I would say, especially in the past 5 years or so, there's a lot of places where I think we have fallen short. So I understand why people would think it's just hype. But I would say if you look at the actual scientific progress that's being made, the literature that's coming out, which is not as accessible as marketing blogs. So a lot of people don't do that and don't get to see it. But if you look at like the scientific papers being published that are on like the archive or in scientific journals, and you also look at roadmaps from major companies like IBM, but there are others as well, and you keep track of how well they fulfill their promises, then I think you'll see that it's not all hype. Like we would not be putting this much effort into something and checking off those boxes that we promise consistently every single year if it was just hype.
Awesome. And then the next question is, um, do you or IBM work with companies on real use cases? If yes, could you share some of them?
Sorry, what was the last part you just said really quickly, Secretary?
Oh, yes. If yes, could you share some of those use cases?
Oh, sure. Use cases. So one of the ones I'm really interested in are chemistry, materials research, I think those are sort of like near term applications. There's some cool work that we're doing with companies like Boeing to explore materials and try and come up with different optimizations of alignment in material structure. Batteries are a really good example. And then there's also optimization in finance, which I think is really cool. I'm not as familiar with finance, I'm not a finance person. But I think the idea of like portfolio optimization and fraud detection in finance, which quantum computers could be really good at, is very interesting. So those are just some of my favorites, but there's so many.
Agreed. And then have there been moments when your outreach efforts discovered new research questions or collaborators?
Collaborators for sure. So yeah, I guess in that way we have come up with new research questions. We've had some really good collaborators that we have discovered from people basically using IBM systems. But like we would see the paper and we would think like, oh, well, that's a really interesting technique. I wonder if they thought of trying, this additional method, or maybe they started going down this path, but we would recommend this path instead. So we have found collaborators that way, and we have been able to answer some interesting research questions and basically explore new topics that we wouldn't have just by ourselves, which I think is really the point of what we're doing and science in general. Like, we don't want to only be the sole providers and gatekeepers of knowledge. We want as many people involved as possible.
Awesome. Now switching into technical questions, what might the results of a triple slit experiment be? Quadruple slit?
Oh, yeah. If you had a triple slit experiment, you would just see a different type of interference pattern. It would just look like different squiggles, depending on like the size of the slits and how close they are together. That's actually probably more important for like the type of pattern you would see than like how many there are. They've done multiple triple, quadruple slit experiments. It doesn't really matter how many they are. The underlying principles are still the same. Yep.
Awesome. And then have there been any advancements in the philosophical implications of the development of quantum mechanics?
Yeah, I think so. I think one of the more interesting things that we're going to learn in the next few years is in the philosophical realm umbrella. One of the things that I explored in graduate school that I would say was experimental but also philosophical was the idea of weak measurement. And again, I just like measurement. I think it's really cool. But what we're used to when we talk about measurement in quantum mechanics is strong measurement or projective measurement, which is a total collapse of the wave function into a classical state. But a weak measurement is basically like when you measure something a little bit and you learn a little bit of information instead of like all the information. So I didn't know that that was possible. And the fact that you can do it not just theoretically, mathematically, but you can do it in a lab to a qubit, I think has some interesting philosophical implications. Like, what does it mean to measure something a little bit? So, I mean, there haven't been like any grand results. Like, we haven't solved the measurement problem. We don't know what the collapse of the wave function actually really means yet. But we have learned some things, and I think we'll learn more.
Awesome. And then this next question is about measurement. The measurement problem remains one of the most fundamental open questions in quantum mechanics. If this problem is someday resolved and we succeed in discovering the exact mechanism behind collapse, or develop new mathematical tools that allow us to predict which state a particle will collapse into, does that mean superposition was never truly physical, just a mathematical artifact? And two, the entire probabilistic nature of quantum mechanics would break down since we no longer need probabilities to describe outcomes.
So we know we need probabilities to describe outcomes. We know that part is true. We don't know the underlying mechanism that I guess can make you picture what entanglement is, but we know it's probabilistic. So that part isn't going anywhere. So I don't think it's quite as uh, negative as maybe you explained in the second half of your sentence. But I do think it's possible that one day we'll learn more and we'll have more of a conceptual understanding. I just don't think it's going to change the underlying mathematical structure because we know that that mathematical structure and how we conduct experiments using it is the most accurate and predictive scientific method that exists. So I don't think that's going anywhere.
That's good to know. And then we have a couple questions about observables. If you could explain them again and how estimators impact them.
Yeah, so an observable is just something that you can measure in a quantum experiment. So the most classic examples are like position and momentum, but you can also measure phase. You can measure, the state of a qubit. These are observables. Not everything can be measured, and certainly not everything can be measured simultaneously. So when we talk about expectation values, we also talk about which types of observables can be measured at the same time. Like phase can be measured at the same time as some of the other ones I mentioned, but you can't measure position and momentum at the same time precisely. That's where we get the uncertainty principle from. I hope that answers
Awesome.
it.
No, that's a really good explanation of it. And then how many particles in nature are already entangled and how did they get that way?
Oh, I have no idea. I don't think oh, that's a good question. I have no idea how many particles in nature are entangled. I'm not sure if there are any. Uh, Probably there are, but you can create entanglement from a wide variety of mechanisms. So I don't know how you would tally that. Sorry.
Um, yeah, I guess we should go out and start counting now if someone hasn't already. But to switch frames a little bit, going into a group of questions people are having about is it too late to start quantum computing if I am already in like established field? Is it too early to start quantum computing if I'm a beginner? Do I need a PhD?
Yeah.
Um, what is your take on that?
I mean, I don't think it's ever too late to learn anything. If you're, looking for a job in the field and you're 1 year away from retirement, I might be like, why? But I don't think it's ever too late to learn anything new. Um, some people might say, like, is it too early? And I could see that argument being made. Like, I do see high schoolers asking us for internships a lot, and we don't accept high schoolers. It's a little too early for you, just because of the law, to like actually dive into a career in it. But that doesn't mean you can't learn independently and get started and build up your fundamentals if you think it's interesting. I don't think it's necessary. And I think no matter where you are in your career, like I said, unless you're like a year from retirement, it's not too late. It's never too late to change career paths if you find something more interesting. So no, I don't think there's like a definite timeline that you have to follow.
Awesome. And then do you think people need to get a PhD to get
Yes.
involved?
That was the other part of the question. No, I don't think so. You don't have a PhD, right? Not yet,
I
seems
don't have a
green.
PhD, no.
So look, she's here. She's doing great. Yeah, you don't need a PhD. It depends what you want to do. If you want to be like, a leading researcher in error correction, and be like, yeah, you kind of need a PhD for that role. But there are plenty of roles that don't require PhDs for sure.
Exactly. And for context, I'm a product marketing manager, and there's roles across the stack from the business side to the software side. So don't necessarily need a PhD if you don't want to get one right away. And then the next questions are sort of around what is the current state of quantum computing and what can we expect in the next 5 to 10 years?
Yeah. So in the next 5 years, I think what we're really looking for is that those experiments that prove quantum advantage. And I'm using the term proof loosely here because I think when quantum advantage results first start emerging, it's going to take a while to verify them. Because one of the things we have to do is sort of wait and see how classical methods are going to respond, because it is sort of, a race where one is overtaking the other and then back and forth. But that's to be expected. I think that that's what's going to happen in the near term, like 5 years. And then if you look to 10 years and further than that, the important things that we're going to see are like fault tolerance quantum computers and universal quantum computers emerging. IBM has a plan to do that up in our Poughkeepsie lab in New York in 2029. So you can read a little bit more about that on our blog if you're curious. And then after that, I would think that quantum solutions would become ubiquitous. Whether people working in technology or industry know they're using quantum solutions, I'm not sure, because I think part of the interesting way that we're going about things is that we are creating supercomputing infrastructures that will be designating jobs to both classical supercomputers and quantum computers. So it sort of will just give the workload to the type of computer that is good at solving that type of problem. But I think, in the next 10 years, this becomes pretty commonplace.
That's so exciting. And I feel like those advancements are happening across the stack, hardware and software. So there's a place for everyone to contribute. So with that, we're at time. One last question for you, Olivia, before we let you go is what is one lecture or lab that you're really looking forward to for Kiskit Global Summer School?
Um, so one thing that I'm really looking forward to is Patrick Rawls' lecture. I think it's next week. So you're gonna have to stick around for a while. Patrick is just such a good lecturer. I've learned a lot from him recently. I've been working with him a little bit to understand more QEC stuff. He's a pure theorist, and I'm really pure experimental from my background anyway. So I've learned a ton from him, and he's a really masterful lecturer, and I think you'll really enjoy that one.
Awesome. Well, thank you so much for being with us today, Olivia, and thank you to you all for asking all of these amazing questions. Keep that excitement and enthusiasm with you as we go throughout Kiskit Global Summer School. And yeah, thank you guys.
Thank you guys so much.